In the previous lecture, we presented extensive experimental data to demonstrate clearly the fact that the turbulent boundary layer of the mean velocity in external flows or internal flows exhibits a universal structure, and the universal structure consists of two regions. One is the sublayer, viscous sublayer, adjacent to the wall or the nose strip boundary, and the lower region, which is the overlap region that lies above the sublayer. Although there is an outer layer, the outer layer does not exhibit a universal structure. This was what we saw in the previous lecture. It was also demonstrated that the velocity profile in the sublayer as well as the log region, for example, for values of y from y equal to 0 all the way up to y plus sub 350 is given by this expression where the constants b and kappa are known. Now in this lecture, what we will do is to see how this universal structure, particularly this expression, proves to be of tremendous use in carrying out numerical simulations of complex flows using Rand's equations. We saw earlier that the Rand's equations, which are given here, govern the mean velocity field in a turbulent flow, U bar, V bar, P bar, and the W bar. And so the fact that the universal structure exhibited in turbulent boundary layers can be used in Rand simulation should not be very surprising. In fact, it should not be surprising at all. Let us see how they prove to be useful. Now, any any Rand simulation that is done on a complex problem, for instance, external flow over an automobile or some other shape, or internal flow in a complex geometry, usually has a very important requirement, and the requirement is that the numerical solution should be able to give a very good prediction of the wall shear stress on no slip surfaces. So there may be multiple no slip surfaces, and the numerical solution should be able to predict the wall shear stress on the surfaces quite accurately. The requirement is critical because the wall shear stress is used for calculating skin friction drag in external flows and pressure drop in internal flows. Now, in the case of turbulent flows, this requirement is actually quite challenging since the gradient of velocity is very steep near the wall. So calculating wall shear stress the wall shear stress basically is mu du bar dy, and as we saw in Klebanov's experimental data, the wall shear stress mu du bar dy is quite challenging to compute in numerical simulation because of the steep gradient in the u bar velocity profile near the wall. So consequently, we need to actually have a lot of, if we are to resolve this gradient, notice that U bar drops from about, as I said before, 0.6 to 0 in a span of y over delta 0.005. If we have to resolve this gradient, then we need to use a lot of mesh points within a very, very small region, in addition to the mesh points that we have used elsewhere. And when we do that, what can happen is excessively large number of nodes is required, and as a result, the overall increase in the number of nodes may be so high that doing 3D simulations may be prohibitively expensive. It may not be possible at all. So if you want to get a good estimate for the wall shear stress, the number of nodes that are required may be so high that it is not possible to carry out simulations of three-dimensional flows. And most flows of engineering interest are three-dimensional and turbulent. Okay, so this is actually a vexing problem which we need to address. Now, it turns out that we can circumvent this difficulty by based on our knowledge of the universal behavior of the sublayer and the log law region, in particular, the fact that we actually know the velocity profile in this region through this equation. So what we do is we try to make sure that when we discretize the domain, the first node from the wall is placed at such a distance that it lies within the outer edge of the overlap layer. Although the overlap layer, as we mentioned earlier, goes all the way up to y plus of 350, to be on the conservative side in practical simulations, we try to make sure that the first node lies at y plus of around 100 or less than that. So that is what is done in practice. Once we do this, we can actually exploit the law of the wall to get a very good prediction for the wall shear stress as follows. So here I have illustrated the procedure in a pictorial manner. So here we have the velocity profile in a turbulent boundary layer. Notice the very steep gradient near the wall. And if you try to resolve the velocity profile in this small region, far more number of nodes would be required between this node, which is right now the first node from the wall. Far more number of nodes, perhaps 10 to 20 more, will be required just in this small region. Although 10 to 20 seems like a small number, in the case of a three-dimensional simulation, 10 to 20 along each x equal to constant or y equal to constant grid line can add up to hundreds of thousands of additional nodes, if not millions of additional nodes. So this really is a very difficult requirement to satisfy, and this gradient really is very difficult to resolve. So what we try to do in practice is to make sure that this first node, which is labeled 1 here, so here we show a close-up view of this region. So what we try to ensure is to place the first node from the wall. So the wall is here at y equal to 0, and this node is labeled 0. So we try to make sure that the first node normal to the no-slip surface is placed in such a way that it falls within the universal region. It could either be the logarithmic overlap layer, or it's also possible that it falls within the viscous sublayer, or it could fall within the buffer layer. That is possible. So we make sure that it falls inside this region where there is a universal behavior and the velocity profile is given by the law of the wall. So the basic idea is that, since the velocity variation in this region is given analytically by the law of the wall, I don't actually have to resolve the remaining part of this velocity profile at all. So this profile, which is very, very steep and very difficult to resolve, need not actually be resolved because I already have an analytical expression that describes the velocity profile. So this is how the law of the wall comes in useful for doing practical RAN simulations. So the fact that we don't have to resolve this is actually is a very important fact, and that is what makes it possible to carry out realistic three-dimensional RAN simulations over complex objects, whether external or internal flows. So that is that's a key breakthrough in that sense. Notice that although I'm not resolving this part of the velocity profile, we know for a fact that the velocity goes to 0 at y equal to 0 because the expression that we have, analytical expression, satisfies that condition identically. So when you set y equal to 0 in this, the value for u automatically goes to 0 without any problem. So y equal to 0 is automatically satisfied. The no slip boundary condition, u equal to 0 at y equal to 0 is automatically satisfied. And we also do not have to resolve this using nodes in this region because this behavior is known analytically. So that is how we exploit the law of the wall. So in a practical implementation, there are many ways to implement this in a practical computer code. One way to do this is to do something like this. So I know my y coordinate of the first node from the wall. So knowing y1, and let's say that I have a current value for the axial velocity at this node. So we actually know the y coordinate is fixed, and let's say during some intermediate level of calculation, I know the velocity at this node. So based on y1 and u1, I can actually go into this expression. Notice that if I apply the law of the wall at y1 on the first node, I get this expression. The only unknown in this expression is the friction velocity, or indirectly the tau wall. So I can solve this equation to get the tau wall. And in the next iteration, when I am going to update my velocity field, what we do is we apply this wall shear stress that we calculated from here as a boundary condition. Notice that y equal velocity equal to 0 at y equal to 0 need not be imposed because that is automatically satisfied. So what I do is I have a current value for axial velocity. I know y1. I evaluate wall shear stress from this expression, u star and then wall shear stress. And then I impose this wall shear stress as my boundary condition on the wall rather than u0 equal to 0. So we carry out the calculation one more time. We get a new value for the velocity at the first node, and we repeat this procedure. We get a new value for the wall shear stress, and we keep doing this. Eventually, when the calculations converge, the value for the wall shear stress that we get from this and the U1 for the given value of Y1 are such that this is satisfied exactly. So now we are able to not only satisfy the no slip condition, namely u0 equal to 0 at the wall, we are also able to resolve the or calculate the wall shear stress quite accurately without resolving it by using the fact that the first node lies within the within the region where the turbulent boundary layer exhibits a universal behavior independent of Reynolds number. Of course, some adjustments have to be made to this expression depending upon the actual type of flow and so on. But those are details which can be worked out. The basic idea is that we choose not to resolve this because the behavior is already well known, provided the first node lies within the region where the turbulent boundary layer exhibits the universal behavior. So by using this procedure, we satisfy not only the no slip condition on the wall, we are also in a position to calculate the wall shear stress very accurately, which makes the computation tremendously useful.